Hello everyone, welcome to my channel. By the way, to those who are new, I am Engineer J. I am a civil engineer and I am also currently teaching as an engineering professor. And in this video, we have a new topic. We have here a simple linear regression analysis. So this is a topic or one of fundamental topic in statistical analysis. Now, what is the use of a simple linear regression and how we use it or where to use it in the real practice? Okay, so by the way, what is a simple linear regression? So simple linear regression, this is a statistical method that allows us to summarize and study relationships between two continuous or quantitative variables. So simple linear regression is used when you want to measure the relationship between two variables, such as if you want to know the relationship between x and y, or let's say you have the size of your waist to your height. Okay, like you want to measure the relationship between your weight to your height and so on. So that is the use of simple linear regression. But in actual practice, we use simple linear regression in prediction. If you want to predict an outcomes given that we have a predictor. Okay, so like for example, you have a two variable. We have your weight, that is your predictor, or that is your independent variable. Okay, and knowing your weight can be used to determine your height. Okay, so this is just an example, but in simple linear regression analysis, we will be trying, or we will be knowing how strong these two variables correlates to each other. Or it could be our if you want to predict unemployment rate given that we have a population. So if there is a relationship between unemployment rate and the population in a country. So that's how a simple linear regression works. But why is it called a simple linear regression? By the way, we have different regression analysis. We have a multiple linear regression analysis. We have also a exponential regression or exponential distribution. We have also a logarithmic regression. But in simple linear regression, the only difference is that we have only one variable x. Again, x here is our predictor or our independent variable, and we have only one variable y, which is our y here. This is our response outcomes or our dependent variable. So basically, the value of our y depends on the value of our x. Hence, it is called dependent variable. Okay, so that's why is it called simple, since again we have only one dependent and one independent variable. And it is also called linear since again this equations here resembles to a linear equation, which is we know we have y is equal to mx plus b. Okay, so we will be using this equation to compute for the value of y given that we have a value of x. But before that, we need to know the value of coefficient b and the constant a. So before we can come up with the equation, it is important that we compute first with the coefficient b and the constant here a. Okay, so we use the formula from the methods of least square. Okay, the concept of regression analysis deals with finding the best relationship between y and x, quantifying the strength of that relationship, and using methods that allow for prediction of the response values given values of the regressor x. So we do not stop by just developing a linear equation. So we measure how y and x correlates, or how strong the two variables correlates to each other. Okay, and we also measure how effective this equation in predicting the y variable. So if this equation can be used for prediction, or this equation can be effective in computing the variable y given a variable x. So that's what we are dealing here in this topic. Okay, so we compute the coefficient of correlation, the coefficient of determination, the standard error, and the standard deviation. Again, our goal here is to develop a equation of a line, okay, or the linear equation. So we have method, what we call the method of least square. Now we can determine b here by following this formula. We have n here is the number of a sample, then summation of the product of x and y, and minus the summation of variable x times the summation of y variable over, or all over, the number of sample times the summation of the squared of x variable minus the squared of the summation of the x variable. So that's how we compute for the value of b. Now, to compute for the value of a, we just use this formula in which we have the mean of y variable, or the mean value of y, minus the b, that is the variable, or that is the coefficient of the mean of x variable. So that's how we compute for the equation of the line, which describes the relationship between the predictor x and the response or the outcomes y, or the dependent variable. Okay, so we have also the coefficient of determination. This one measure that assesses how well a model explains and predict future outcomes. So this value of coefficient of determination can be used whether the equation that we just came up is effective in predicting future outcomes. Okay, it is indicative of the level of explained variability in the dataset. So it indicates the percentage of the variance in the dependent variable that the independent variable explained collectively. So if we have a coefficient of determination equals to 1, that means 100% of the variance of the dependent variable explained by the independent variable. So therefore, they have very strong relationship. Okay, so coefficient of determination varies from 0 to 1. Okay, so 0, that means that our equations, the simple linear equation that we developed, can't be used for predicting future outcomes. Okay, so the greater the value of r, that means the effective our linear equation would be. Okay, so we have the formula for coefficient of determination. We have SST, that is the total sum of square. We have the formula in which the formula for total sum of square is the variable y minus the mean y. Okay, then minus the error sum of a square. Okay, so later on I'll teach you how to compute for the SSE over the total sum of square. That is the coefficient of determination. Okay, so again, coefficient of determination measures the predictability of the equation or the linear equation that you developed. Okay, we also have the coefficient of correlation. Now, coefficient of correlation measures the strength and the direction of linear relationship between two variables x and y. The linear correlation coefficient is sometimes referred to as the Pearson product moment correlation coefficient, in honor, of course, of its developer, Carl Pearson. So as what you can see, coefficient of correlation, it is just the square root of the coefficient of determination. So we have r is equal to the square root of the coefficient of determination. Okay, or the square of coefficient of correlation is just the value for coefficient of determination. Again, coefficient of correlation measures how strong the relationship between the two variables. Okay, so we have the value of coefficient of correlation varies from -1 to +1. Okay? Now, if the value of R is equal to 1 or equal to -1, that means the equation or our data creates a straight line. If we connect all the data x and y, they create a linear or a straight line. So that's how if we have a value of y, but in reality we do not have a perfect correlation. Okay, so we have the formula, which is this one. Now again, we have the value of R varies from -1 to +1. The positive and negative signs are used for positive linear correlations and negative linear correlation respectively. When we say positive correlation, if x and y have a strong positive linear correlation, R is close to 1. An R value of exactly 1 indicates a perfect positive fit, or if our line or if our data forms a straight line, if we connect them all. Now, positive values indicate a relationship between x and y values such that as values for x increases, values of y also increase. So positive correlation means if x increases, the variable y also increases. Negative correlation meaning they have opposite in direction. If our x increases, y decreases. Okay? And -1 indicates a perfect negative fit. When we have R is equal to 0, that means there is no relationship between x and y variable. Okay? So there is no linear correlation, or there is a weak linear correlation between the two variables. A perfect correlation of positive and -1 occurs only when the data points all lie exactly on a straight line. That's as what I have said. Okay, and the positive and negative, this is the slope of the line. Okay, we have R when equal to 1 or -1, that means we have perfect correlation. If R is greater than 0.8, that means we have strong correlation. If R is lesser than 0.5, that means we have weak correlation between two variables. And if we have R is equal to 0, there is no correlation between the two variables. Now we have this line of best fit, which shows how the two variables y and x correlates. Okay, so this line shows the correlations between the two variables. As what you can see, as the points lies closer to our regression line, that means we have strong positive correlation. But if our points or our data points of our y and x lies farther from the line or from the regression line, that means we have a weaker positive correlation. Now, positive correlation, since again we have the same direction of y and x. So as our x increases, our y increases as well. So they have a positive slope. Now for this one, this is a negative correlation because as what you can see, as our x increases, our y decreases. Okay, so that means we have a negative correlation. But this is strong correlation since as what you can see, our data points lies closer to our line of fit. Okay, so the farther the points from the line, that means the weaker the correlation would be. And we have for no correlation when we have all the points are scattered. Okay, just like this one. So in no ways it creates a straight line. Okay, so there is a varying value of x and y. Okay, so again, this is a best fit or the line of fit which measures graphically the relationship between x and y variable. We have what we call the standard deviation. Of course, we already know what is standard deviation. This is the distance of the points with respect to the mean, or how far or how dispersed, how spread the points with respect to the mean. Okay, how scattered the points are. And we also have a standard error. Standard error, this measures the error or the difference between the actual value and the estimated value. Okay, or this is also known as the residual error, or represents the average distance that the observed values fall from the regression line, or that measures how far the points is from the line of fit. Okay, so gaano kalayo ang point from the regression line. So let's try to solve problem. Okay, so I have this problem here. Determine the linear relationship, the data gathered from the pretest. So this is the score for pretest, this x values here, and the score for post-test. So let's say this is person A, person B, C, D, and E. So these are their scores. So person A during the pretest, he or she got a 95% score, but during the post-test, he or she got a 85% score. So we will be trying to know here if given their grade on the pretest, can we actually predict their post-test grade? So that's how we are trying to prove here, or we will be developing an equation that can be used for the prediction, or that can be used to forecast the value of their post-test grade. The first thing we do here is to we will be using the formula, this formula here, to compute for the B. So we will be needing, or we should compute first the value of xi squared and the summation of their product. So we add another column here. So this is the squared of the x variable. So this is their grade during the pretest. Okay, so the squared of 95, we have 9025. The squared of 85, we have 7225. The squared of 80 is 6400. The squared of 70, we have 4900. The squared of 60 is 3600. Okay, so we squared the variable, or all the data from the variable x. Then, since we will be needing with the product of x and I, so we multiply the grade x and the grade y. So 95 times 85, we have 8075. We multiply 85 and 95, so we have their product 8075, and the same as with the other remaining rows. So we multiply the variable x and the variable y. So and then we sum up, we add the value of x, all the value of x, so we have 390. So we sum up all the values of y, so we have 385. We sum up all the values of x squared, so we have 31,150, and we sum up all the product of x and y, we have 30,500. So we substitute this value here to our formula. So we have this formula here from the method of least square. So again, we will be developing a linear equation here, which is y is equal to a plus bx. So using this formula, so we have n, our n is the number of data. So we have 1, 2, 3, 4, 5. So we have 5 data, and the summation of the product of x and y. So we have here 30,500. Okay, then minus the summation of the value of x. So we have here 390 from here, and summation of y, we have 385. So we have 385 here over the sample, then summation of the squared of xi. So we have here 31,150 minus 390 squared. Okay, where 390 here, this is the summation of x. So we have now the value of our coefficient b. B here is 0.6438. So we have now the value of our coefficient b, which is 0.6438. And now we compute for the constant a. Okay, so to compute for the constant a, we will just be needing this formula. We have the mean of variable y minus the coefficient b times the mean of variable x. So we compute the mean. So we have the mean x here is summation of all the x over n. Again, that is our mean x. So we have 390 divided by 5, so we get 78. And for the y, we have 385 divided by 5, then we get 77. So that is the average. So from there, we have 77 minus 0.6438 times 78, then we get the a, which is 26.7836. So we have now the equation that explains the relationship between the post-test and the pre-test. So we have y is equal to 26.7836 plus 0.6438x. So we can use this formula or equation to compute for the possible grade of or the possible post-test grade given their pre-test grade. So we can predict the post-test grade if we have a value of their pre-test grade. Okay, so however, we need to know if this equation is reliable or if this equation can be used for future analysis or for future use. Okay, so by just knowing their coefficient of correlation and coefficient of determination. So we have to compute for the coefficient of determination, so we compute for the SST. Okay, we have yi, that is the value of the post-test, minus bold y here. Again, this bold y, this is the mean. Okay, so we have, let's say for the first row, we have 85 minus the mean. The mean is 77, then squared, then we get 64. Then for the second row, we have 95 minus the mean of y is 77 squared, then we get a value of 324. Okay, and the same procedure for the rest of our data. So we get now the SST and the result. If you add all the value for SST, then we have a 630. Now we compute for the standard square error by just computing the difference between the actual value and the estimated value. This estimated value here can be computed using this equation. So we have, for the first one, we have y is equal to 26.7836 plus 0.6438 times 95 is for the first row. This would give us the estimated value of the post-test grade. We have 87.9446. So we can now compute this value by using this formula, yi minus y. We have 85 minus this, our actual value, minus the estimated value. We have 87.9446, then squared. Then we have here 8.671. Okay, so never mind the difference in their decimal. So we have now for the second value here, so the same procedure, we compute for the estimated value. Y is equal to 26.7836 plus 0.6438 times the x value here, we have 85. This would give us the estimated value equals to 81.5066. So we can compute their SSE by just getting the difference between the actual and estimated value, then squared. So we have here 95, that's the actual value, minus the estimated value 81.5066, then squared. We have here 182.072. Okay, so again, never mind the error in decimal point because I used Excel to compute for this. So Excel used the exact values, including the decimal points. Okay, so the same procedure all throughout the data. So we have now the SSE as the summation of all this value, and our SSE here, or that is the sum of a square error, which is 327.396. So we have here SST, which is 630. SSE here is 327.396. Okay, so we can now compute the coefficient of correlation using this formula. R is equal to square root of SST minus SSE over SST. So we substitute all the values. This would give us coefficient of correlation of 0.693. As what you can see, we have above average correlation, or not too strong but not too weak correlation. And we have coefficient of determination, which is just the squared of the coefficient of correlation, and that is the squared of 0.693, which is equal to 0.480. Again, the closer to 1 determination, that would give us a effective linear equation, but as what you can see, we have a smaller coefficient of determination, but we have a lot of factors that contributes to this value, and that includes the number of a sample. So in order to get a perfect linear equation, okay, so you need to have a greater number of sample. As much as possible, this is more than 100, and that would give us a much reliable equation. But as what you can see, we have a smaller coefficient of determinations, and that is because we have only 5 sample here. And this explains that 48% of the variance of our post-test, or our dependent variable, explained by the independent variable. So hindi ganun karami. Okay? And then we have the standard deviation. Now standard deviation, again, this measures how far the data they dispersed from the mean, or how far the data, or how scattered the data is with respect to the mean. So we have this value here. So the result is 11.1803 by just using this formula, square root of SST over n minus 1. Okay, and here is the number of a sample. And the standard error here, again, standard error measures how far the actual value from the estimated value. Okay, so this is important since this also measures how effective our line of fit, or how effective our equations. Now if we try to plot our data, we have again this data here, pre-test, and this one is the post-test grade. So if we plot this one, this red dot here, this is our scatter plot. So we have the first coordinate here, 95, 85, so 95x and 85y. So this one here, okay, we have 95, 85. For the second value, we have 85, 95. So 85, 95. So this one. We have 80, 70. So this one here. 80, 70. We have 70, 65. So this one. And we have 60, 70. So this one here. So this is our scatter plot. But if you try to plot this equation, okay, this linear equation here, so this blue line here, so as what you can see, so our scatter plot here is trying to create a linear, but not that too close to our line of fit, since again we have a very low coefficient of correlation. Okay, but as what you can see here, they are still correlated somehow, since again they form, or they are not too close but not too far from the line, okay, or our regression line. Again, this regression line here is from, or it's generated from this equation, y is equal to 26.7836 plus 0.6438. Okay, so that is our line of best fit. So in conclusion, Simple linear regression is used to predict something given that we have a predictor variable or we have the independent variable, and it is used in forecasting data. Again, thank you guys for listening. If you have questions, please comment it down. Please don't forget to subscribe to my channel. Thank you guys and stay safe.